Good evening. Welcome to the sixth lecture of this lecture series, Physics with Partha. Let's quickly revise our previous class. In our previous class, we have learnt Maxwell's speed distribution law, where we have seen a bell-shaped curve giving us V maximum, V peak, then average velocity, etc. Then we have learnt thermodynamic state, equation of state, and Brownian motion. In Brownian motion, we have seen a visual of this Brownian motion. Okay. In today's class, we are going to talk about phase transition, vapor. As you can see in the picture, attached picture, this depicts a vapor. So there is some difference between gas and vapor. Though in our observation, we cannot differentiate it in our normal observation, but scientifically, the vapor and gas are different. We will learn what it is. Then we will talk about isotherm, explaining what are isotherm and critical temperature. Okay. Let us see phase transition. As you can see, the attached picture shows the three phases of water, that is solid, liquid and gas. We can see that from solid to liquid, the conversion process is called fusion, and liquid to gas, it is called vaporization. In this process, water absorbs energy and transforms from solid phase to gas phase ultimately. And in the reverse way, it can condense to liquid and it can solidify to solid state. For this process, it releases energy. So let us talk about the same thing in terms of pressure temperature curve. In this curve, we can see that up to triple point, it is solid phase left hand side. The red curve shows the solid phase portion. Then it enters into liquid phase, and below the blue curve, it is vapor phase. Above the blue curve, it is liquid phase. And again, it is important to note that this vapor phase, liquid phase or solid phase, the phase transition again depends upon pressure as well as temperature. The combination of two make us observe this curve. Then it is written that compressible liquid and supercritical fluid. In supercritical state, it cannot be compressed anyway. And supercritical state, we are not going to that. Then at critical point, we see the right side of that line shows us gaseous phase and left side shows liquid and vapor phase. And there is some point written, two important point is written. One is triple point, one is critical point. What it is, we have learned already. Triple point is the point where all the three states, that is solid, liquid and vapor, stays at equilibrium. And what is critical point, we will talk in this lecture in a detailed manner. Let us check the difference between gas and vapor. The gas is a substance that has a single defined thermodynamic state at room temperature, but a vapor is a substance which coexists with liquid or solid at room temperature. Room temperature, that means 25 degrees centigrade. Okay. A gas is a substance above its critical temperature but below its critical pressure. But a vapor is a substance above its boiling point temperature. For example, gas, we can tell that helium, argon, etc. And vapor is normal, as we all know, water vapor. So what is gas and what is vapor in terms of the latest shown diagram phase transition curve, we will again revisit in our calorimetric class. Okay. For this class, it is sufficient to know just that gas and vapor is different, and how it is different, it's important. Okay. Now let's talk about vapor more. When we assumed some postulates in ideal gas, we have assumed that the gas molecules do not exert a force on each other except for the time of collision. But in reality, the gas molecules assumed to be hard spheres. They exert an attractive force on each other. At low pressure and high temperature, average separation of gas molecules is large. At that condition, the attraction energy will be small and average kinetic energy will be more. But when pressure increases and temperature decreases, as we can see in our previous curve, when pressure is increasing and temperature is decreasing, then it comes to solid phase. Okay, attraction energy becomes more dominant and gas liquefies, and again if we go to lower temperature and higher pressure, it comes to solid phase finally. Now if temperature T is large, then kinetic energy is large. It's obvious. So no amount of pressure, if temperature is sufficiently large, then no amount of pressure can liquefy the gas. The temperature above which this behavior is observed is called the critical temperature of the substance. That means the temperature above which we cannot liquefy the gas is called as critical temperature. Okay. Now a gas below its critical temperature is called vapor. Okay. I think by now you are clear about what is vapor and what is gas. Okay. Let's talk about isotherm. In the attached figure, this is taken from NCERT book, I think chemistry book it is given. Then we can see that in this picture, different curves are written at some particular point of temperature. As we can see from the upward side, 50 degrees centigrade, 31.1 degrees centigrade, etc. is written. So these are curve. In y-axis we are plotting pressure, in x-axis we are plotting volume, and we are plotting different curve at some particular temperature. For one curve, temperature is remaining constant. We are observing the behavior or relationship between pressure and volume. So over a curve, if temperature remains constant, then it is called a isotherm. Here the figure, again our drawn figure shows that for each curve the temperature has remained constant, and that is why they are also isotherm, and the process over this curve is called isothermic process. Okay. So we can observe a bell-shaped curve joining the other isotherms. Okay, that bell-shaped curve is called phase transition curve. Over this curve, phase transition takes place, and here we can see some points are written A, B, C, and D. So in our next slide, we will discuss about those points and reasons specifically in detail, and the red arrow shows the increasing direction of temperature in our left hand side figure. Okay. Before explaining the hand drawn figure, let's quickly talk about Andrews PV isotherm. Here the picture shows the same kind of isotherm we are observing since last 3-4 slides. Okay. So we are written here we have written that right hand side of the semicircle, dashed semicircle, as we can see in the figure represents the gas phase. Inside the semicircle, we have gas and liquid coexisting, which is vapor phase. So vapor phase is the phase of coexisting gas and liquid below the critical point. That means the gas is still can be compressed. Now then if we move left in the x-axis, we are compressing more and more, and finally liquefaction process is complete at the left edge of that semicircle, and we have written that liquid phase is there. Now even for very single small compression, we need a very large pressure. That is why the curve is almost vertical straight line at point C to D. We can see curve is vertical straight line. That is why. Then curve T3, curve at temperature T3 and T4, they represent ideal gas behavior. That means all the postulates of KTG are followed, and these curves as it represents, they are not liquefying, they are ideal gases. That means whenever gas is liquefied, the interatomic interaction should be there. But as we have assumed in KTG, for ideal gases no interatomic interaction is there. That is why it behaves that way. Okay. Now let us explain the water isotherm. As we can see that the green arrow shows points to 350 degrees centigrade. So we can see the isotherm of 350 degrees centigrade goes from A to B, then B, C, D, like that. A, B, C, D, these points represent the state of the system, as you can see in the attached picture. Okay. At point A, water is in gaseous form. Now if we increase pressure, keeping temperature fixed, then state changes to B, that is point 360 degrees centigrade, point B, at 163 atmospheric pressure. Here liquefaction starts. From point B to C, the water will undergo liquefaction. No further increase will be there in pressure, but volume rapidly decreases. Then state C represents the entire water is converted to liquid. From that point onwards, that is point C onwards, towards point D, a large pressure is needed for a very small compression event. That means after liquefaction has happened, after that we need a lot of pressure for even a small compression. Okay. Let's talk about critical temperature in a more rigorous way. So I want you to look at the star, the red colored star written in the picture, drawn in the picture. Okay, critical temperature as it is written, check at 360 degree, 370 degree centigrade isotherm. Now the liquefaction start at higher pressure. If we compare our previous case, that is ABCD isotherm at 350 degree isotherm, the liquefaction started at a lower pressure of 163 atm. But in case of 370 degree centigrade isotherm, the liquefaction starts at a higher pressure of 194 atmospheric pressure. That means when temperature is increased again, that means when temperature is increasing, the liquefaction process begins at a pressure which is greater and greater. Now, after 374.1 degree centigrade, the isotherm does not enter into the bell-shaped curve. That means water cannot be liquefied at a temperature greater than 374.1 degree centigrade. However much or whatever large pressure we apply, water cannot be liquefied. From vapor or gas phase to liquid phase, we cannot convert water to liquid phase. However large pressure we apply at or greater than 374.1 degree centigrade. Okay, so now water is in gas form only. At greater than 374.1 degree centigrade, water will be in gas form, and below it, that is 374.1 degree centigrade, water will be in vapor form. It will be existing in vapor form. Now simply a vapor is a gas which can be liquefied. That means a vapor is a state of gas which can be liquefied by increasing the pressure without changing the temperature. Without changing the temperature, we can liquefy the vapor. This is again another definition of vapor and a distinction between the gas phase and vapor phase. That means if something is in vapor phase, it can be still liquefied. Now, whenever it does not enter into that bell-shaped curve, then it cannot be liquefied and it will exist in gas form only. Whatever large pressure we are applying, we cannot liquefy this. Okay, thank you. Let's quickly summarize what we have learned today. We have learned about phase transition depicted in a pictorial form. Then we have learned about vapor and the difference between gas and vapor. Then we talked about isotherm. Next, we explained water isotherm and critical temperature. I hope whatever topics we have discussed today is clear to you. And if you have any doubt or query, you can ask in the comment section. Okay. In our next lecture, we will talk about evaporation and some detailed explanation of this phase transition system we will learn in calorimetry, and there we will be learning the calculation related to this phase transition, from where you can expect some question in any of the examination. Okay, thank you.